day, I'm Dr. T and welcome to my office. So today I would like to talk a bit about accounting, chemical accounting to be precise, what's known as stoichiometry. So the goal here is to look at what we know about chemicals and answer a question that's a little bit different than the ones I've tackled so far. I have so far mostly looked at qualitative discussions of chemicals. What are they? How are they made? But now I want to jump into a quantitative discussion. How much do I have? And stoichiometry is the core of this. This would be asking questions such as, if I have these reactants, how much of my product am I going to make? Or if I want this much product, how much of my reactants do I need to make it? Likewise, if my product also is produced with something I don't want, or I have a waste byproduct, in my chemical reaction. I make two things, one I want, one I don't. Well, how much of the thing that I don't want will I be getting for a certain amount of stuff that I do want? And thus, then I can take steps to deal with the thing I don't want. Alternatively, if I want to have this much reactant of one type, how much of another type do I have? So I'm looking at relationships between them, and I'm looking at quantities, which can be profoundly helpful in a multitude of situations. Although usually there's kind of a couple of other steps involved in understanding why do I want these numbers. But in order to go that far, we have to get to how do you get the numbers. And to do this, the core is going to be the balanced chemical equation. Now I say the core because it's not the start nor is it the finish, but it is definitely an integral component. The balanced chemical equation is telling you on an atomic level or a molecular level what the ratio between your reactants and products are. So if I have one where one reactant has the invisible one, it's not written, but there's a 1 there, and another reactant has a 2, then I know that it's a 1-to-2 ratio between those. Likewise, if say a product has a 3 for its coefficient, then I know that there's a ratio of either 1-to-3 or 2-to-3, depending on which ones I'm looking at. So this is going to allow me to have a ratio of these, and fundamentally this is what I need. I know for this product I will, for every one of these I'll get 2 of that other product or whatever. However, these are atoms, or specifically I should say formula units, whether they be molecules if they're molecular formula, or they be the formula unit from an empirical formula. It's whatever the formula style that you put in the equation is. But these are individual atoms, so they're occurring at a minuscule scale. Atoms are absolutely ludicrously tiny, so we need a way of just dealing with the numbers, because we are talking quantities that are, billions of billions of billions potentially. And thus, we need a number that's really, 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 really ridiculously big. And the number that we use is known as Avogadro's number. It's a little bit over 6 times 10 to the 23rd, which is, a lot. It's a very precise number, and it's set up really as a conversion factor. And it converts as a way that we use to count our atoms. So atoms are too small to count. You will never be done counting the atoms or molecules in even a tiny amount of substance. So we have to have a more efficient way of counting. And we count our atoms and molecules by weight. So the principle of counting by weight is the weight of a single individual, the average weight, because individuals vary, but the average weight of an individual, the weight of the total, and you simply divide the total weight by the weight of the average, and that tells you how many individuals are there. This is how we count everything from crackers in your cracker box, seeds, and atoms. The reason Avogadro's number is Avogadro's number is this is the conversion factor between grams and daltons. 1 dalton is going to be 1 gram divided by Avogadro's number. Therefore, I can look at a periodic table, and from that periodic table, I can know the formula weight, which is essentially the atomic weight of all of the atoms in that chemical formula added together. So if I had something like calcium chloride, I would have the atomic weight for the chlorine the atomic weight for the other chlorine, and the atomic weight for the calcium, and I would add those three together, and that would be the formula weight, the weight of that chemical formula. You'll also see formula weight referred to as molar mass or molecular weight. The meanings have slight differences. I typically use formula weight because you see that quite often from the chemical industry, specifically, the chemical suppliers. Additionally, it's distinct, unlike a couple of the other units like molar mass and molecular weight, which we have too many M's in chemistry as is. So formula weight is a nice refreshing, it's not an M, and it leads to less confusion. But yeah. So what we're going to be doing is we're going to take one way of doing this, I should say, because there's several, and I'll be talking about the others in other videos. We're going to take the weight of the one chemical that we want. So we weigh that chemical out, we divide that by its formula weight, and that tells us the number of moles of that chemical. We're using the formula weight, which will be expressed in grams per mole, and we're using that as a conversion factor. So then we take the one chemical, we divide it by its formula weight, although we usually do dimensional analysis, so it's not just strictly divided. We divide it by its formula weight, then we multiply it by a ratio that is derived from our balanced chemical equation. So it's going to be the chemical that we're starting with. That's going to be in the denominator, because remember, dimensional analysis is what you want divided by what you got. And then the numerator will be the coefficient from the chemical that you're trying to convert to. So you're going to have both coefficients, the one you're going to on top, the one you're going from on bottom. And then if you're going from weight and trying to predict weight, then you would use the formula weight of the new chemical, the one you're trying to convert to. You would multiply that formula weight in that dimensional analysis chain, and then that would give you grams of the chemical you're trying to find for. If you started out with a reactant and the chemical you're trying to find for is a product, then that is what we call a theoretical yield. It's called theoretical yield because that's what you should be getting. It does not necessarily mean that is what you will get. Typically, we're imperfect, we're mortal. Nothing happens perfectly. So typically your actual yield, what you actually go into the lab, you do the experiment, you make the chemical, and the amount of chemical you actually make is slightly lower than your calculated theoretical yield. The ratio of those two, actual yield divided by theoretical yield, is known as the percent yield. So actual divided by theoretical times 100%. That gives you percent yield. And that's a way of describing how good your actual reaction was. Ideally, it would be almost 100, very, very close to 100. Obviously, if it's over 100, something went wrong. Usually, you've got some solvent or some contaminant in there. But in other cases, under 100 is understandable. But, that meant your chemical did something weird. It went away. So that may or may not be acceptable, depending on how close to 100 you are and exactly what you're doing, because, everything is context specific. When looking at this, theoretical yield has a couple different ways of looking at it. Obviously, if you're just looking at one reactant turning into the product, that's the standard theoretical yield. Sometimes you'll be looking at having two different reactants mixed together, in which case you can calculate the theoretical yield for each one of them, unless they are in what we call a stoichiometric ratio, where they're in just the perfect ratio, so both of them will react fully and produce product. Unless they're in that stoichiometric ratio, then one of them will run out first, and thus that will limit how much product you can make. Its theoretical yield will be slightly lower than the other one, or potentially greatly lower. It depends on the ratios. Its theoretical yield will be lower. That's the one that we call the limiting reagent. All other reagents that would be left over are called excess reagents. So if I've got two things, unless they're in that stoichiometric ratio, then I would say one is the excess, one is the limiting reagent. The limiting reagent is what governs my theoretical yield when I do that. So with that said, this is a brief introduction of chemical accounting, what we call stoichiometry, and I will see you in later videos. Have a wonderful day.